This lesson we're looking at stationary points. Now, stationary points, the thing of the word stationary means it's still or it's not moving. So in terms of a graph, and what we're looking for is when the rate of change is zero, or the graph is neither increasing nor decreasing. So if we just took any function, so let's look at a cubic like this, then when we looked at the derivative, we know the derivative is the gradient at a single point of that tangent line. So if I picked this point here, there's my tangent line, the derivative at that point would give me that gradient. So from, let's say this is point A here, and this can be point B. We can see as we're below point A, that no matter where I draw that tangent line, it's going to have a positive gradient. When I get to point A, it's going to give us a horizontal line. And we know the horizontal line, from our linear equations work, the gradient would be zero. So if we're thinking about this as something in motion, we'd go, well, it's increasing, and then when the gradient is zero, it stops. In between points A and B, we can see that we get the tangent lines would all have a negative gradient, but then when we get to B, we're going to have another zero. And then when we're greater than B, we can see it is positive again. So what that means is that the gradient at these 2 points here would be zero, and that therefore they're not decreasing nor are they increasing, so we'd call them stationary points. So stationary points are when the derivative is equal to zero. So stationary points occur when the derivative equals zero. Now, that works for any of those points, whether they're maximum minimums or points of inflection. So if we had another cubic like this, then we'd have a positive tangent, and then at this point, there'd be a point where it is zero, and then it goes positive. So let's look at an example equation or function and see if we can find its stationary points. And we'll use our Desmos to check as well. So let's use a cubic. Let's say f of x equals x cubed minus 4x squared minus 3x plus 20. And let's just look for the stationary points when x is greater than 0. So we know cubic functions. We can see the general shape from those two that I drew there. It could take those forms. We want to find the stationary points. So find stationary points. So first things first, find the derivative. So we derive this 3x squared minus 8x minus 3, and the 20 would drop off. And we can see here now we've got a quadratic that we need to factorize. So we can look for factors of 9 that add up to negative 8. So that should give us 3x plus 1 times x minus 3. Just quickly check that. That will give us 3x squared minus 3. So that would be minus 9x plus x is minus 8x minus the 3. Yep. So that should work. So that's our derivative. So to find the stationary point, we need to solve this equal to 0. So using our null factor law, we say what x value makes these brackets zeros. So therefore, x could equal positive 3, or over here it would be negative a third. And we're going to ignore that one because we only want it when it's greater than 0. So stationary point occurs at x equals 3. And you go, I'm done. However, we know that any point should be given in its coordinates form, so you need the x and y values. So this x equals 3 is the x value of the stationary point. However, to find the y value, you must sub it in to the original equation. Make sure you don't sub it into the derivative because we want to find the point on the original function where that stationary point occurs. So we're trying to find f of 3, not the derivative at 3. So we'd have 3 cubed minus 4 times 3 squared minus 3 times 3 plus 20. So we'd get 27 minus 36 minus 9 plus 20, which would give, didn't mean to draw that, which would give us That'd give us -9 minus 18 plus 20 gives us 2. So therefore, the stationary point is at our x value of 3 and a y value at 2. So let's check that using Desmos. So here's my equation, x cubed minus 4x squared minus 3x plus 20. So if we sketch that, we can see there's our cubic function and our stationary points. We can see there's a negative a third that we found, but we're not worried about that one. We just want to find this one down here, and you can see it appears at 3, 2. So now, when we're sketching functions, we have a way of finding our local minimums and maximums, but also our points of inflection. So we call them all stationary points, and we find when the derivative is equal to 0 to find the coordinates. So for this equation, we can see there's our stationary point. We notice we rejected that 1/3 because in the question I was only asking for the positive, but if you had to find all of them, you could sub in negative a third to find that other stationary point. Okay. Hopefully that made some sense, and we'll continue from here next lesson. All the best.